And now we are in this wonderful position to welcome Arnaud Doucet, Professor of Statistical Learning in Oxford, Senior Research Scientist at Google DeepMind. So a person that lives in both worlds, and I will bring the perspectives perhaps of a mature scientist with a lot of experience in industry in the generative AI space to us. We are very much grateful to have Arnaud Doucet with us. Arnaud, the floor is yours. Thank you so much.
Thank you. So I can use the pointer. Oh, how do I get this thing to start? No, that doesn't work. This one? Yeah, this one works. Okay, thanks for the invitation. Basically I'm going to talk about the work that has been done, like basically 100% at Google DeepMind, with a bunch of collaborators that we list later on. And particularly the main author on this paper is Yaxin Shi, who's actually written the best slide of this. So I'm sure a lot of the audience here is familiar at least with some of these diffusion models, which are at the core of the generative AI revolution. And so basically, we'll talk about that also today. But I will basically talk about application of these techniques to discrete data. Okay, and as we'll see, it's extremely challenging actually to make those techniques actually work for this type of data. So that's the core of the talk. Okay. So I didn't know who the audience was for this talk. My understanding is that it's a mix between ground public and scientists. So basically, I will start with just kind of very simple, kind of basic introduction to generative AI. An introduction to the kind of standard, I would say, diffusion model. Okay. And then we will see how, if we are careful, we can adapt this kind of techniques fairly straightforwardly to discrete data. And actually, we'll see that we are able to obtain state-of-the-art results for a variety of interesting tasks. Okay, so I mean, we've heard a lot about generative modeling so far, but what is it mathematically? Well, I'm going to give you a very unprecise definition, which is I give you a bunch of data from some kind of unknown distribution pi. So think of it as a collection of images or a collection of text. And you just want to generate new data, new sample from this unknown distribution, which are approximately from pi. So they look like some of the one you have in the audio database, but are not carbon copy out of them. Okay, you want some kind of innovation somewhere. All right, so that's been used a lot in machine learning over the past 12, 15 years. Is one of the main topics in machine learning, with like techniques also like reinforcement learning or meta learning, but that's one of the core topics in this area. And why people are really interested in, so they use it to basically generate synthetic observation. So in particular, it's used when you want to train like complex system. So you want to train like a complex neural system so as to develop self-driving car, and you don't want to have to record hours and hours of videos, but you just basically use like synthetic data that are obtained via generative AI. They've been used actually also a lot in the context of inverse problem. So basically, you're interested in reconstructing corrupted images, and you want to follow a Bayesian approach, which is standard, obviously, in the inverse problem community. If you follow a Bayesian approach, you need some kind of prior. I mean, in the old days, people used to do Markov random field, this type of really, I would say, priors that are actually nowhere close, they don't look like, nowhere like the natural image. So now we say, hey, instead of using this kind of like mathematically convenient, but really not very good prior, let's use this kind of generative model that are really very, very powerful data-driven prior distribution. So there's been a lot of application in the context of generative modeling. Okay. So because it's such a big area that people have been working on that like now for a very, very long time, so I list some of the techniques that have been proposed so as to address generative modeling. So there was like, I just the energy-based model, that's something that even started in the mid-90s. Variational autoencoders, normalizing flow, generative adversarial network, which were introduced in 2015, an extremely popular class of generative modeling. But all these techniques were superseded, actually, in the context of, as we say, image, video, and audio synthesis by denoising diffusion model. Okay, so what are those techniques? Well, so first, just to say that they are very recent because they were first introduced in 2015, but already the two papers that kicked, really that started the whole area were from 2020 and 21. Okay, it's just like they are used absolutely everywhere. Okay. So this is like the papers, that are like, for academic paper, if you're an academic, you look at the paper that's been published in 2020, that's 10,000 citations. It's actually incredible, actually, okay? And I gave this slide, I gave a talk, actually, 3 weeks ago in the machine learning conference. The second paper had 10,000 citations at the time. So in the 3 weeks, it had 550 more citations, actually. So this is to tell you that basically, people have basically jumped on this class of models. They are using them absolutely everywhere, actually. It's just like, all the applications you can think of, people are basically working on them. Okay, so give you some application that you might be already familiar with. So there's been obviously application to image synthesis, so DALI 2, DALI 3 now by OpenAI, Midjourney, ImageGen by my colleagues at Google. There's been things to do audio generation, music generation with Udio. You might have heard of them recently in the news. For video generation, we've had Sora by OpenAI, and my colleagues at DeepMind basically have been developing Google VO recently, or Stable Diffusion. Okay, so basically anything that is related to image, video, speech, music synthesis, most of it nowadays is just basically developed using this kind of techniques, okay? So that's actually quite impressive. And why? It's just simply because they provide empirically remarkable performance. It's state-of-the-art performance. Okay, so that's nice. Okay, and it goes beyond media. So that's actually an interesting thing. So I would say you're more interested in the science application. Well, it turned out the kind of same techniques have been applied to protein structure generation, and there again, they provide state-of-the-art results. So there's this paper of Nature by some of my colleagues, and we had a collaboration at MIT as well, where we showed that actually this thing can provide actually useful new protein structure that have been synthesized in the laboratory. So that's all nice, but what about something I haven't discussed yet? What about like text? So when you use like Gemini or ChatGPT or Claude or all this Llama, all these things is text data, is discrete data, okay? So are those methods, you could say, are this basically models based on diffusion model? Well, it turned out that no, okay? So I'm just gonna make a thing, is that diffusion models are not state-of-the-art for discrete data. So this is really one key area where really they are outperformed by these autoregressive pre-trained transformers. So we had an introduction, a very nice introduction on beyond an introduction by Arnaud this morning, but this is a case where really they are not doing that well yet. And it is not because people haven't tried. There are literally over 1,000 papers where people are trying to apply this type of ideas to discrete data, and it turned out it hasn't been really successful so far, okay? So this talk, we're gonna try to close the gap, okay? It's just a step toward closing the gap. We see that the approach we have followed is actually very, very simple. There's really nothing complicated mathematically, nothing as complicated as Arnaud has presented this morning. It's a very elementary math, but we see that actually it still allows us to close the gap with respect to current existing model. So what have people been doing so far? Okay, so the first thing they did, they say, well, okay, so, this kind of discrete data, if I want to directly apply the denoising diffusion model to discrete data, because they were developed for real value, data, well, you cannot really apply them directly. So the obvious thing you could do is to embed your discrete data in a continuous state space and just use diffusion in this context. So there's a lot of people that have done that. So we have a paper with Sander Dillman at DeepMind, or many other people from DeepMind. It's called CDCD. There was paper by people at Stanford, Play, Bit Diffusion by Jeff Hinton, where people are trying to do that. and it's kind of work okay, but it's not great. It's not really competitive also to transformers. And one of the reasons is that really, so you have this, you project your discrete data, you have this embedding, but the moment really you use this kind of like diffusion, this embedding space, it doesn't seem to do really anything really sensible. Okay, it's not like when your image, when you're trying to, you have this kind of image and you add noise in the kind of standard denoising diffusion model in this context, the kind of nice story where you destroy the high frequency first and then the slow frequencies in this context. Nothing like that, actually. So you can do it, and it kind of works, but not quite. So we thought, okay, what about doing something else? So instead of really trying to embed that in RD, we could do say diffusion of the simplex. So we'd think of a single discrete data. You could think of it a token. Okay, you're going to put it like you're going to encode it as a one-hot vector, and it's going to be correspond to a vertex of a simplex. And you kind of do a diffusion on the simplex. Okay. So we did that. I think we are the first to do that at DeepMind, again with Sander Dillman and Pierre Harvey Richmond. And there were a lot of other papers actually that appear closely after. There was in particular the Bayesian flow network by Alex Greif, which corresponds to doing this kind of things. It's a different way to do it. There were people doing it. This is called that directly diffusion, where people were doing that. They had good application for things like DNA sequencer, generation, but for text, we managed to get decent results for translation, still not working really well. Doesn't really do very, very, very well. You could say, okay, maybe, instead of trying to force this kind of continuous structure on those discrete data, why about working directly in discrete data? And people have been looking at that as well. I mean, it's not like, I said, it's a very, very active research area. You can believe that, if such an obvious idea obviously would have been explored. So yeah, there was a few papers. There was a paper from my colleague at DeepMind, actually, where they did that, actually, an influential paper in 2021, where they essentially tried this idea of denoising diffusion, which I explain more mathematically later on. They tried to generalize that to discrete data, and there was more recent paper in Stanford by the group of Vernon, Score Entropy, where further they kind of keep on pushing things, but still we are not quite there. Okay, so yet it's really important somehow, area. We'd like to be able to scale, to be able to implement those methods for discrete data, but it's not yet there. Okay. So one thing we'd like is that essentially we're not quite happy with the current way people are doing text generation. So I'm just not going to go through all the detail, but one of the things is that we're having this kind of autoregressive structure. And essentially, there's this belief that, because it's autoregressive structure where you predict the next token given the past token you've generated, somehow, whenever you make kind of a mistake at a given token, it's too late. You can never recover. Whereas if you had this kind of like more denoising diffusion structure, because essentially you generate the sequence essentially jointly, you wouldn't be exposed to such issues. So that's one kind of intuition why people are so keen to do this kind of diffusion for text as well. And also the other thing is that if you try to do this kind of denoising diffusion for text by going and embedding in continuous state space, and you want to do tasks like in-painting. So what does it mean in painting for text? Is I give you a bit of text, okay? Like you have the first paragraph, the third paragraph, you try to just basically in-paint fill what the second paragraph should be. It doesn't work well. You need a lot. You can make it work, but it requires a lot of fine-tuning. So that's not quite good because a lot of things we want to do when we do this kind of text generation is somehow what we call kind of conditional simulation. You give me a prompt, and then basically you're gonna basically give me some kind of the continuation to this prompt. Okay? So that's why also it's interesting to do that. Okay. So that's a thing. So what we're going to present in this what I'm going to present in this paper is a kind of, I'd say, an approach that partially closes this gap. Okay, there's no claim that we are yet at the level of the autoregressive pre-trained transformers, but we're getting there. Okay, so the paper is called Simplify and Generalize Mass Diffusion for Discrete Data. So that was a project that was initiated by Yaxin Chi, Keyang Han, Zi Wang, myself, and Michalis Titsiats, all people working at DeepMind. So you can find the paper on archive. So we posted it in June, just after the NERIF deadline. And literally in the following week, there were 2 papers doing pretty much exactly the same thing that were developed by one team in Cornell and one team in China. So some of the ideas were wrong, okay? So that's not, okay. So to start with, basically to introduce this kind of model, what I'm gonna do, I'm just gonna basically first start introducing the kind of standard ideas between the noise and diffusion model in the context of RD. And we're gonna try to use very similar idea to do things for discrete data. It's very, very simple actually. Okay. So unfortunately, I don't have a video here because it's not on my laptop. So here, if I had the video, what you would see, it's a nice video that were developed by Yang Song in this 2021 paper, where you have your original data. So for the time being, think of just images. Okay, so, and later we'll think of text actually. On what you do, you have your clean images that are your training data, and you're gonna basically noise them progressively, such that eventually they are like just noise sample. Okay? And at the distribution level, what it means is that you have the distribution of the data, which is going to be typically, highly multimodal, very complex distribution. And because you add this kind of noise, eventually this distribution is going to be transported to a Gaussian distribution. So here, for a simple example, where the distribution would be on the real line and would be bimodal, and you would apply this diffusion across time. So here is the time index. And essentially, this bimodal distribution would be essentially transported to Gaussian distribution. Okay? So this is a kind of very simple, incremental mechanism where you destroy the information that is given by your original observation. And the key idea of denoising diffusion model is to say, well, you have one single way, this kind of incremental way, to essentially noise the original information and transport your data distribution to the Gaussian distribution. So if we could implement somehow the reversal of this transformation, then we could start from noise and get back to data. So that's really exactly the idea. So again, if you had the video here, what you would see is I start from noise sample, I do the kind of reversal of the noising mechanism, and I will explain a bit more mathematically what I'm doing, and eventually I would obtain samples which are approximately distributed according to the data distribution. At the kind of distribution level is that you would basically start from the Gaussian distribution, which is the noise distribution, say in this context, and you would reverse, and eventually it would be transported to the original data distribution. Okay, so how do we do that? So I have multiple introduction to denoising diffusion model, and I'm going to follow here an approach which is going to be very useful because it extends straightforwardly to the discrete setup I'm interested in. So this approach is the so-called variational diffusion model. It's a paper by Kingma, Salimans, and other people at Google. Basically, they formulated it in a kind of simple way. So it is completely equivalent to the standard formulation of the denoising diffusion model. It's just a kind of formulation that makes our life easier. Okay, and he said, okay, what are we doing actually? What we are doing is that, say you have X is your clean data, okay, at time 0. And essentially, you generate some Markov process, okay, which essentially such that the state ZT is a noise version of the clean data X, okay? And eventually, it's just a pure noise sample, okay? So what we are doing is we are defining actually practically a Markov process so that the marginal distribution of ZT, that is the noise version at time t of X, given X, is a Gaussian, so of argument ZT, mean alpha Tx on variant sigma t squared times identity. And I pick alpha T, so alpha T initially is 1, and then it goes to 0, okay? So, sigma t squared goes what? It goes from 0 to 1, okay? So what it means is like essentially close to t equals 0, this thing is roughly a Gaussian of mean x on variance very small, almost 0. on close to time t equal 1, this thing is just a standard normal distribution. That's all it is, okay? Okay, so you can rewrite that. Again, you can say, well, if you have that, you can rewrite essentially, you can parameterize things in terms of signal-to-noise ratio. It'll be useful in the equation later, where essentially the signal-to-noise ratio is defined as alpha t squared, which is essentially the power, essentially the energy of the signal, where x is like standardized to start for simplicity, divided by sigma squared, the amount of noise. So essentially what you have is that close to t equals 0, the SNR explodes to infinity, and at t equal 1, this SNR is 0. So you have SNR that decreases actually. You know is more and more your data. Okay, so this is kind of, you have this forward process you define, essentially, this Markov process. And what you want to do mathematically when you try to do this kind of denoising is just you're trying to simulate from the time reversal of this Markov process. So you're trying to invert this transformation. You look at this Markov process and you try to basically simulate the time reversal of this process. Okay? So to do that, what I need to compute, if I want to simulate from this kind of time reversal of this diffusion process, what I need is I need to compute to approximate expressions such that the conditional distribution of the state Zs given Zt for S inferior to T. So you have, say, here a noisy, so this is a noisy version of the original signal X at time T, okay, Zt. And you want to basically go to a time which is inferior, so you want to denoise essentially little bit the noise version of the signal at time T to go to a less noisy version at time S, okay? So, and if you could simulate this basically this Markov chain, or in continuous time this Markov process, you would get back to, at time 0, to a sample from the data distribution, right? So that's all we are doing. So you have this noisy mechanism, the forward Markov process, it knows more and more my data, and really what I want to do, if I want to go from noise to data, I just basically need to approximate this kind of time reverse transition that denoise the process progressively. Good. So when you look at that, you say, how am I going to approximate that? It seems not really trivial. Well, it turns out it's not so difficult. Okay. So what we look at is that we have a very specific structure. Okay. So essentially, what I can write as basically what? So this is the integral of the conditional distribution of Zs given Zt on X, the clean data. Integrated with respect to the conditional, the posterior distribution of X given the current noise version, the noise version of X, Zt, X. So here, this shouldn't be X naught, it should be X, I apologize, okay? There's a typo here. Okay, so that's what we need to do. So you see, what's the point now? This thing is known. This thing is known because I'm just dealing with very, very simple, basically linear Gaussian noisy mechanism. So if I know X, the initial distribution, this thing is just a Gaussian density with a mean which is a kind of weighted linear combination between Zt and X on a variance I can express analytically. So this bit is completely trivial to express. I can do it analytically. What is this bit? So well, this is somehow my posterior distribution of the unknown X given the clean data given its corrupted version at time t, where, okay, I say I have this integral, it bothers me. So what I'm going to do, I'm just going to replace that simply by some kind of point estimate of X given Zt. Okay, so I'm just going to write it here. So here, I just approximate this integral. I just replace this whole integral here by just basically saying, well, you know, Q of X given Zt, you can think as a kind of delta mass that is basically located as some kind of point estimate, which I denote X at Ztt, and it's going to be dependent on some parameter theta that I need to learn. Okay? So that's going to be my approximation of the time reversal, which is something with dependent on parameter I'm going to have to learn from my data. Okay? But that's very, very simple. So we start from this really trivial identity. Just say, well, approximate that by a point estimate, and this is your approximation. Okay? That's it. Okay. Now, what do we need to do? We need to learn this parameter. Okay? So how do we learn this parameter? Well, we're going to say, okay, if I wanted, what's my generative model? My generative model, which I've designed now, is the stuff where I start from noise. This is Z1. And progressively, I denoise the process. Okay, so I have a Z1. I go to Z, with my notation, 1 minus 1 over T. Then I sample Z 1 minus 2 over T, given Z, given 1 minus 1 over T, and so on. I go till time 0. And that's going to generate essentially the data at time X. Okay, so this is a complicated, essentially, generative model because it's given by this kind of time reversal, the marginal of the time reversal of a parameterized Markov process. Okay, so it's complicated. Obviously, you'd like to learn the parameter, so as to do the best on your training data. Ideally, you would maximize the log likelihood on your data, so as to learn the parameter theta. It's kind of just way to learn a parameter, but you cannot because it's not tractable. It's a big integral. So when you have big integral, likelihood which are intractable in machine learning, what do? You do a kind of evidence lower bound. So we are not basically going to essentially maximize the log likelihood. We're going to maximize an evidence lower bound, okay, which is an expression which is given as follows. And for those of you who are familiar with variational encoder, it's kind of very similar. So you have some kind of prior loss, okay, reconstruction loss, but you have an additional, what we call diffusion loss, which is given essentially by some quantity which is fairly intuitive, which involves the expectation of the KL, feedback level of discrepancy, between the kind of conditional time reversal of that corresponding to the denoising process on my parameterized denoising diffusion kernel. Okay? So if you message that a little bit, you can see that this thing is very simple, and it turns out that essentially it's given up. It's very simple expression. It's a kind of weighted, actually, square loss, where you basically minimize the square loss between X and its denoising estimate of X, which, remember, is what was used to parameterize the denoising kernel. Okay? So it's very, very simple. So you have that. You have this simple standard variational lower bound, okay? And, it looks, we took some time discretization here, but it's clearly, you look at the way I've written it, it begs for you to look at what's happening in continuous time. So instead of having, T diffusion step here, if you just take T going to infinity, well, what are you going to obtain? Well, I'm going to show you. Simply, you're going to obtain an objective, which is just a very, very simple objective in continuous time. Okay, so we see that really, if we want basically to learn or process, denoising diffusion process, what we should be doing is actually maximizing this loss, or if you want, minimizing the opposite of this loss, that is this kind of expectation of a kind of square loss function between the clean data on your reconstructed your denoiser estimate at time t on your integrate over t. Okay, so it's kind of very, very simple. I mean, so I'd like to emphasize that I think this presentation is much simpler than what is presented in most of the literature. So we see that the way we've proceeded, just to summarize and forget about the detail because it's not that important, you have a very simple noising process. That's the important thing. Then it has a very, very simple structure. And because it has a very, very simple structure, okay, you're in a scenario where the time reversal of this Markov process, really what it is, you can rewrite it as this kind of conditional distribution, which is given in closed form because it's a very simple noising process. And basically here, what appears is somehow the denoiser, the kind of best estimate of X given the current state at time t. Okay? So what we do simply is that we kind of just approximate that by this very simple expression, and we maximize the elbow, and that's it. Okay? And that corresponds to what people are doing in denoising diffusion model. Okay? So it's a very, very simple strategy. Okay? So can we do that in discrete state space? I mean, that's a question. So this is what we're going to do. So I'm telling you, I'm going to follow the identical strategy for discrete data. So for discrete data, well, I'm going to consider discrete data which are, somehow they are nominal data. This is not like arising from some kind of discretization, say, of the real line, associated to each variable, some kind of dummy token, ABC, whatever, okay? The vocabulary is going to be, say, the vocabulary, so finite state space. Say I'm interested, so each thing here represents a discrete data point. So what I'm going to do, I need to consider simple noising process. But somehow, because I don't have really any kind of order, it's not like you can do something like having something that looks like corresponds to doing like a discrete version of Gaussian noise. I mean, it doesn't make any sense actually in this context. So you have two things you could be doing. You could say, well, perhaps I could just basically diffuse toward a uniform distribution on my finite state. Okay, why not? Or you could do something which is even simpler, which is use this masking strategy. So essentially you say, well, my state is going to be clean until a random time at which it's masked. Okay, so I have a symmetry state, if you want, an additional state that I've added to my original state space, and suddenly I'm masked. Okay, and that's all I'm going to do, actually. So we're going to do that for each token independently. Okay, so we're going to have we have a bunch of text, so we have whatever, 100 tokens, and independently, at random time, they're going to be corrupted, so they are clean till at some random time, they're getting corrupted. Okay, so here we go. So here, this is first time I'm looking at, so three tokens have already been masked, and so on and so forth, still at time when everybody is masked. Okay, so what's the conditional distribution, essentially, of the transition, of the transition kernel of the associated discrete state space Markov chain? It's going to be alpha t times the identity plus 1 minus alpha t on essentially the vector that masks everything. So that really corresponds to the equivalent to the scenario where alpha t is going to decrease as well. So this is the equivalent of the scenario in the Gaussian state space, continuous state space. We're having, at the beginning, basically, I'm almost clean, everything is at very, very small noise. In this case, I've masked only very, very few tokens, and eventually purely noise, purely Gaussian noise, and in my case now it's everything has been masked. Okay, that's all. Okay, so that's it. So there are various things you can play with the masking schedule, and it does have an influence on the performance. Okay, now, yeah. Yeah, it's.
Going independently, but there's a constraint.
Just makes our life much simpler mathematically. But yeah, you could do something more general, but actually we've done things more general. You can also have masking rights which are dependent on the token, but for the timing, it's just everything is independent token-wise, and they have same masking right.
So in terms of Markov chain, rather than ending up with noise, you're ending up with a
mask. Yeah.
So everyone ends up with the same.
Yeah, exactly. Exactly. What's the transition associated to this guy? For the time you go from time S to time T, S is always inferior to T. Well, essentially, with probability alpha T over alpha S, you stay unmasked, okay? With probability 1 minus, and otherwise you basically become masked. That's simple, okay? So that was for an unmasked token. If you're masked, you can only stay masked. Okay, so this thing was only for an unmasked token. Okay, if you're on a mask, yeah, there's no choice, you're masked forever. Okay, so you see that actually there's something which is not very pleasing with it, is that in the context of continuous data, you have like this continuous degradation of some of the signal, but here it's literally either you're clean, either you're completely masked. So it's not quite the same yet. Yeah, so we did that. So we did that as well. So first, it's not as simple in terms of objective. You can do it, but the objective is becoming more complicated. And as a result, we found it doesn't perform as well. Actually, that was yeah. That's what just a symmetry point. Yeah, exactly. Yeah. 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 So remember what we're going to need to do later on is to come up with an approximation of Q of x as given xt. So the reverse. That was the forward, I want the reverse. And remember what I was doing when I was doing with continuous data, I was writing the reverse is the integral of the reverse conditional upon x, the clean data, time essentially the integrated with respect to the posterior distribution of x given the noisy version at time t. So they're going to do exactly the same thing now. We're going to say, okay, what about this kind of conditional distribution of x's given xt on the clean data point at time 0? Well, because it's very elementary, Markov chain, we can write it. So we can say, well, this thing with probability, alpha s minus alpha t over 1 minus alpha t, you get a mask, and it means that then your state becomes x naught. There's no choice because you're conditional upon x naught. When you unmask, you're x naught. That's it, finish. Okay? With probability, otherwise you stay mask. Okay? But we have a very, very simple expression for this actually conditional time reversal when it is dependent on x naught. In our case, obviously, you don't know x naught, so the key is going to be exactly similar to what we did for continuous state space. When you're going to have x naught, you're going to replace it by a point estimate. That's it. It just doesn't go beyond that. Okay? So this is what we're going to do. So we're going to have essentially, we're going to learn, so remember x naught, we use this kind of one-hot encoding. And what we're going to basically learn, so the equivalent of the denoiser in this context is going to be learn essentially the probability that essentially the unmasked token at time t is equal to set j. Okay, so that's all. And we just plug that into our conditional time reversal, which is strictly equivalent to what they were doing in variational diffusion model. Exactly the same. So you do that, and then you get back to the evidence lower bound, because similarly define a kind of generative model which is completely intractable because it's literally the marginal, the final time marginal of time reverse Markov chain with parameterized transition. It's not, you cannot compute this marginal distribution analytically. So if you want to estimate the parameter theta of your denoiser, you're going to maximize instead the elbow. And similarly, because everything is very nice, you can take the continuous time limit, and this is what you end up with. So this is a very, very simple criterion. It's a very simple criterion, which is nothing but some kind of weighted cross entropy. That's all it is, actually. Okay, so that's actually quite nice, is that literally the only thing we've been doing is essentially we're just optimizing weighted cross entropy, which means that this is a criterion that is extremely stable to optimize, contrary to what could be what we found in the literature. Okay, but so that's it. So this thing here, I made my life simple because here I was presenting the equation when you have only one token. Okay, in practice you have n token, where n is the number of a character in your text. In which case, what you get to optimize is not, you don't have to train one actually classifier. If you want the denoiser, you have n of them. But the resulting evidence lower bound you need to optimize is again simply a sum of weighted cross entropy. So again, a kind of very, very well behaved actually. And it's some kind of something kind of even more similarity than with what people did for continuous state space. In particular, you can find that basically this kind of criterion is only dependent actually on the equivalent of the SNR at the endpoint, where the SNR is defined for this kind of discrete data as follows. Okay, so I'm just going to skip that, but it's actually quite interesting. There are very, very nice similarity with what people did in discrete in continuous state space. Yes. So yeah, for masking, people use maskgit or muse, which is related to diffusion but different. But people have been using that. So the model Fenaki, for example, this is something that has actually used for the kind of video on YouTube, video generation, use some kind of masking mechanism for images, actually. This is not quite the same, but this is this kind of ideas as well. Okay. So there are multiple interpretations of this thing. Okay. So the first thing I say, well, is that I think for me is the kind of easiest thing the way to think of it is that it's just a discrete version of this kind of variational diffusion model. And in a sense, you see this is really already kind of obvious extension. And we see that in a sense, it's perhaps not the way you would have come up with, because somehow it looks a bit heuristic at the beginning. You can make things rigorous, but it's not perhaps the most intuitive things. But we see that if you follow an approach with continuous time Markov chain, which we followed originally, it's actually turned out to be not particularly convenient. Okay, let me go through this detail actually. Okay, so if you are given this problem, okay, and you're coming from my community, the first thing we did when you said we're going to do diffusion for discrete data, you're going to say, well, I'm going to formalize everything very neatly with a kind of continuous, time, discrete state space Markov chain. So you know what I should be doing when we deal with this kind of object. You have to deal, obviously, with the right matrix. Okay, so this is the way you parameterize continuous state space Markov chain usually. So somehow the right matrix, you can think of it as a kind of Taylor expansion of the transition matrix between 2 times t plus delta t. Okay, so you do the right matrix for the noising process. You have the kind of right matrix for the conditional, time reversal, and you kind of compute the evidence flow bound for this kind of parameterization. So you have to parameterize the right matrix of the time reversal of the process, and you end up with this kind of criterion. So this is we derived that in a paper with my PhD student Andrew Campbell. There was Valentin de Bortoli, George Janidis, and Benton. Okay, so we did that, and this is the criterion you obtain when you do that. Okay, this is exactly the same criterion as what I have written before for a specific, actually parameterization of the time reversal. It turned out that this approach, when you look at that, it's actually, this criterion is terrible to optimize, actually, okay? Because we didn't realize we could simplify it at the time, because it involved, for each token, you have to sum over all the elements of the vocabulary. It's extremely expensive, so we came up with trick to kind of like not having to compute all this sum, and it was extremely high variance. So somehow, although it's actually exactly the same result, essentially, that you can manipulate and play with this criterion. We get back to our criterion. In a sense, it was not obvious at first on this criterion as written as follow. It's very difficult to optimize. Okay, so that's a problem. And similarly, when you look at the way we've derived it, you realize that somehow, what we need to do, we parameterize everything as our time reversal as a function of this kind of denoiser, whereas what people have been doing typically when we're doing this kind of time reversal for continuous state space, discrete state space continuous time Markov chain was parameterizing the infinitesimal rate of the time reversal, which involved this core, which is this kind of ratio of marginal distribution. Okay, in a sense, the way you realize that the parameterization people have been using is actually don't enforce some important actually constraints that are verified by the true model. It turns out that this has implication in terms of optimization and in terms of performance. So the kind of very silly approach we took, it turned out to be actually have quite a lot of benefit. Okay, so I'm just going to skip that, but basically you can see that if you don't follow this approach, you can end up with criteria which is actually fairly awful. And it turned out, if you know what the answer is, you can get back to what we had, which is just a weighted cross entropy. Okay, so we do that. Let's play on some application now. So there is some application. So what we do is a kind of example of simulation where we start from all mass token and we denoise over 1,000 step. Okay, so here we see the kind of first word that appear, the first token that are unmasked. And in green is that the next token which are unmasked, and then the yellow, and then the red, actually. And we see that basically we have that kind of main words that appear first, and then we kind of fill the gap eventually. Okay. Okay, so we compared in terms of like this kind of measure that people use for language, perplexity. So it's related, in this case, to the minus log likelihood. Okay, and we compare to a variety of model. So GPT-2, which is autoregressive model. Okay, so GPT-2, not GPT-3, just emphasize. So this is really a kind of fairly old model. But on some kind of discrete statement diffusion that I've implemented before, some relying on embedding on OR. So we see a kind of lot of data sets we actually do better in this term of perplexity, actually. There's an exception, which is this kind of lambda data set where it's not yet competitive. Okay. But overall, it's actually quite good. So this is the lower, the better. Okay. So we have a things application like to look at how it does in terms of training. So what we realize is essentially this kind of criterion is that because it's a weighted cross entropy, it's actually much more stable numerically to optimize. So we have much less percent. So for example, the kind of something that was very difficult to optimize is when you try to optimize this kind of discrete diffusion, which works on some kind of embedding of the discrete data in continuous data, where there's a lot of like instability appearing numerically, actually. So that's actually one of the benefits as well on providing actually quite a lot of good results in terms of perplexity. Okay, so other example on text 8, where we see that actually we do better than all the existing discrete diffusion on any other AR, but there's still a gap with the standard, transformer AR, the kind of like things that people are using. So we've closed the gap, we're not yet there, actually. And finally, maybe something which I found really interesting, it was a case where you tried this kind of masking diffusion for images. So for images, there's some kind of ordinal type thing, okay? So we completely ignore that. So, we would think that, it'd be better to use this information to kind of like degrade more nicely the information instead of going from clean, just you go to a mask. You could do something where you just have a little bit of noise, something that looks like much more like continuous diffusion. Where what we found is that yes, you can do that, and we do compare in our paper. But it turns out the criterion is becoming very fiddly to optimize. It doesn't have this kind of night-weighted cross-entropy structure. As a result, we don't get results as good, actually. So that's quite interesting. Okay. And finally, I just want to have this thing on what I call a conditional sampling, conditional generation. So basically, where you have a prompt, okay, that has been given to you, or you just have already piece of text, and you fill the gap. And you could say, well, okay, so we want to do conditional generation. There's a whole literature in the literature for conditional diffusion, which is like, okay, I have this guidance term, and you have like classifier-free guidance. There's a whole literature on that, and that is actually very useful when you're dealing with continuous value diffusion. I think actually Eric will talk about that this afternoon. But here we're going to do something. You can extend that to discrete data. It's probably feasible to extend that. But we're going to do something much, much simpler. So essentially, we treat the prompt or the context as tokens that have been already unmasked actually, and we just run the reverse. We start the reverse process at this kind of as a time that is not the final time. It's just like you look at basically proportion unmasked token over the number of tokens. That's it. That's all you're doing. Okay, so you have the thing, and you start your denoising process, not at time 1, but just at a lower time to account for this token that you consider unmasked. That's it. That's all you're doing. This thing works remarkably well, actually. Okay, so this is our example. So this is result for various schedule. The schedule being this kind of masking right. So here we just have a kind of initial. This is the initial context. And this is what it fills. And here, we just give it the end of the text, and you need to come up with the beginning. Okay. Further on the conditional sampling, where you're given actually this time, 2 bits of a paragraph, and you need to come up with some filling, so text filling in painting. And further, so these are not cherry picks. So the model is actually doing quite well. So it's somehow a step toward closing the gap. But as I say, there's still a lot of work to do to actually hopefully one day be competitive with the existing, autoregressive transformers, which stuff. So here it is. Thank you.
Thank you so much, Arnaud. So, questions? Eric?
Yeah.
Eric, wait. No.
Sorry.
You did not explain much what you put in your function mu fit. There are transformers? Or?
It's the transformers, actually.
Okay.
Yeah, it's the transformers. It's quite key, actually. You need the transformers.
And the second thing is that you don't explain much how you do the positional encoding. So is there kind of additional?
Yeah, there is, but there's not much trick on that. This is really not the key. So that's really, but having the transformer architecture is the key, actually. You really need that, but really, really crucial. There's one thing I didn't discuss also is the way we sample this actually continuous time discrete space Markov chain. So there are various ways to do it. There's a kind of naive way, which is literally some kind of Euler type scheme, which is very simple, actually. But actually, you can do something much cleverer, which is literally, essentially, you can sample the unmasking time before everything and just unroll your process. So it's actually, you can do cleverer things that are actually not, we're going to add in the paper. We haven't added them, but you can do that, actually, which is actually quite useful. Yeah.
Another question?
Hi, a very interesting talk. Do you have a sense of the complexity in terms of training models like this relative to its competitors?
Literally, there's no more complex than like a standard diffusion model, really, or autoregressive pretrained transformers. This is just not really. There's no additional complexity.
Okay.
No, there's no problem there, actually.
Okay.
Yeah.
Thanks.
Okay.
Thanks, Arnaud. So I'm curious, this sort of discrete integration by parts that ends up kind of summing over the vocabulary, is it sort of like a similar thing that you get if you don't do tweedy but implicit score matching and then
Sorry,
get like
sorry, I didn't hear you. Yeah?
like when you do just regular score matching in like continuous, for continuous data, instead of doing the tweedy formula rewrite, you can also do the implicit score matching rewrite, and then you get like the trace of the Hessian term. Is it like a similar
actually,
thing?
you're right. So this thing, you can think of it as the implicit score matching.
Okay.
This thing is the denoising score matching. You can actually, we have a version in the paper with Benton who applies to kind of any Markov process you can think of. So it recovered the denoising score matching for Euclidean diffusion, for Riemannian diffusion, also for this discrete stuff. Okay, but essentially, we're doing something even simpler, because you realize that you can just basically kind of further simplify all these expressions in a very trivial actually form. They're all equivalent. It's all the same loss. Yeah.
But is there somehow, like, I guess I'm curious, like somehow there's, in the continuous case as well, technically, like you never really parameterize the score to be the gradient of something. So you're kind of missing things that the real score satisfies. Like, is there something you think like you can sort of do also in the continuous case?
I mean,
like,
the experience in continuous, like for the continuous diffusion, is kind of useless, basically. People have been trying that a lot.
Okay.
And it just doesn't bring any benefit. I mean, there's been a lot of people trying that, and it's kind of an obvious thing to do, but just no benefits whatsoever. So we didn't kind of look at that. Yeah. I mean, obviously, the score what you need to estimate is this thing. It's really, in this case, is this ratio. Yeah.
Okay, maybe one more quick question. Are we good? No, I think we're good. Okay, excellent.
Thank you.
Thank you again, Arnaud. That was fantastic.